Thanks to the Committee of International Conference on Energy and AI for giving us such a chance to be here, and it is my honor to do this oral presentation. My name is Nanyan, and I'm a graduate student of North China Electric Power University currently. Today, I'd like to share with you some of our research on a data-driven methodology for wind power ramp recognition via imaging. My presentation includes these four parts. Firstly, I will give a brief introduction to ramp events detecting, its significance and related work. Then, I will present our recognition framework. Thirdly, I will show you the experiments and analysis. Concluding remarks will be given at the end of the presentation. Now, let's begin. The rapid development of wind power has effectively alleviated environmental pollution and energy crisis, while the impact caused by its inherent randomness under extreme weather on power systems have gradually been stressed. A critical issue is ramp events, which are thunder and large changes in wind power. How to capture and deal with them becomes one of the most urgent topics. The existing work usually obtains the generated power value first and then detect ramps in the power sequence via a specific definition standards. But these indirect methods often ignore the extreme samples for the purpose of reducing the overload forecast error, which lead to the loss of ramp information and the under-reporting of ramp events. Different from the traditional amplitude prediction at time point, the thunder increase and decrease of power output during a short time is only strongly dependent on the meteorological conditions in the moment. What's more, historical previous power values are not of much reference for subsequent ramp events detection. In this case, the advantage of the traditional recurrent neural network, retransmission of long-step dependencies, fails to be exploited. In the field of image recognition, convolutional neural network could be exploited to capture the local features through small receptive fields, thereby forming feature maps with certain rules and association in a higher dimensional space. This property is consistent with the idea that more attention should be put to short-term condition chains in ramp events recognition. To address the above issues, our paper proposed the imaging-basis wind power theory representations and an adapted approach to automatically remove redundant from raw wind power images and extract valid features to recognize ramp events. The framework mainly includes the following three steps: pixel imaging constructing, adaptive feature extraction, and wind ramp recognition. Firstly, we encode power sequence into imaging with the transition from deterministic values to pixels. The load power sequence is preprocessed and normalized to values between 0 to 1 by min-max scale methods. Then, instead of grayscale images with less information, the picture with HSV mode are applied to depict wind power data. Conversion formulas are decided as follows to approximate how human vision perceives color-making attributes. Next, multiply influencing factors are alternately arranged to make the pixels at adjacent moments more compact and highlight the relevant information in a short time, which adapts to the pixel laws of static images and convolutional operation. Secondly, we introduce a data-driven feature extraction network, which is adjusted from LSNet, a classic backbone network. To adapt small-size images generation, the large-size kernel in the traditional LSNet is discarded, and only three multiple thread cores are used. In general, the closer the layer is to the back layer, the more abstract features can be mined. Only part of convolutional layers has been retained to ensure the validity of the semantic information. In our paper, a downward ramp event is considered to occur if the power change in an hour is at least 15% of total capacity, and an upward ramp occurs if the power change in an hour is at least 20% of total capacity. With this definition, we label the pixel images with three classes: ramp downs, ramp ups, and normal events. Then we trained the above improved LSNet models to calculate relevancy between each local feature and labels, and each relevancy is converted into a form of probability by using the softmax formula. To verify the validity and accuracy of the proposed model, the performance of the proposed model and benchmark models were assessed on a public wind farm dataset in our paper. The rated power used in the definition of ramps is 2050 kilowatts. This dataset contains active power, absolute wind direction, and wind speeds, with a temporal resolution of 10 minutes. Here, we only choose the results on turbine RA0711 as an example. As clearly can be seen from Table 1, the proposed method achieves better performance under any indicator. The accuracy of the proposed model is slightly higher than traditional LSNet, while it obtained a 10% increase compared with traditional indirect methods. It shows that the imaging basis wind power theory representations take advantage of multi-channel feature extraction, and the overload framework can reduce parameters calculation without reducing recognition accuracy. In this paper, we propose a data-driven improved LSNet backbone network combined with interpretable wind power pixel images to mine features for identifying reps with less outlight interference and human intervention. Compared with traditional red detecting methods, the proposed adaptive scheme achieves the optimal recognition performance with higher classification accuracy and lower misdetection rate, which possess a certain practical significance. Okay, that's all. Thank you very much for your kind attention.